I found somebody willing to make our first dialogue video. Would you introduce yourself?
I'm Clark Wells. I'm a professor in the mathematics department here at Grand Valley. How much more introduction do you need, right?
that's whatever you're comfortable with, right? The best mustache in the department, obviously. Right. And I don't give that up cheaply. So, all right, so I asked you if you'd think about like a volume problem.
Right.
And you were willing to just kind of think out loud about how you work through it.
Sure, I thought maybe one of the easiest things to start with volume is a square-based pyramid. The way I think about this, trying to find the volume, there's something called Cavalieri's principle, and it essentially says to find either an area or a volume. We'll talk about volume of an object. All that really matters is the cross-sectional areas and then the horizontal, or not horizontal, the vertical height, perpendicular to those areas. So I like to think about this in terms of, you've seen like notepads that are cubes, but well, what if you had a notepad that was bigger at the bottom and smaller at the top? So I think of it, it's made up of sheets of paper. Right, so we've got all these sheets of paper of different sizes stacked up. And in order to find how much paper is actually there, I just need to know how much paper is in each of the sheets and then add those up.
Okay, that really goes with how we've been talking about integration, kind of thinking about it as accumulation. So if we could figure out kind of the volume of one of these little pieces of paper, add them all up, we get the volume of the whole thing.
Right.
Okay,
so one of the things that I have to be a little bit careful about is that the size of the sheets, of course, is changing, right? And we want to come up with some way to have a formula so that whatever sheet we're looking at, we can figure out what its size is. So let's do something concrete. And let's say that this is maybe 5 centimeters, top to bottom.
Okay.
Okay. And why don't we do, just for fun, we'll do 4 centimeters on each side at the base.
So just in terms of a teacher picking out numbers, I like that you picked out different numbers for the base and the height, so we can kind of see those come up.
Right. Yeah, I had a professor in college once who really helped me understand why that was important, because he didn't. And so he said, and so we will use 2, and there were 2s all over the place, and you had no idea which 2 came from where. Okay. So
I see, I mean, like a problem already. Like, we know how big that kind of bottom piece of paper is. I like that way of thinking about it. Is 4 by 4.
Yep.
But how are we going to know? How do you think about the size of the paper?
I think in terms of what I really need to know is at any particular position, I need to know just one side. Okay. And I think about that. There are lots of triangles around here, and so whenever I'm looking at a problem, if there are triangles there, or I can find triangles, that makes things easier. In particular, I want to use similar triangles. So if we look just at, I know we're talking about sheets of paper this way, but let's think about if we cut right down the middle. So we would have.
So how does that help to think about it cut down the middle?
Because then I'm working with something that is 2-dimensional, and I'm familiar with triangles. So that's going to make it a little easier than trying to figure out what's going on here. Now, a different question is why cut down the middle, right? And
that's true. You could have taken just like the face of the triangle, that pyramid.
Right. It's because we go back to Cavalieri's principle, we're looking at perpendicular height. So it has to be perpendicular to the sheet of paper. And so the perpendicular from the tip down to the base is in the middle of the pyramid, not at the edge.
Okay.
Okay. If we were wanting to look at one of the triangles on the face, we'd have to measure down. We'd have two different measurements going on. We'd have the perpendicular height, and then we'd have the measurement along the face, and they'd be different.
Oh, okay. So that makes sense too. If we want to think about adding up from 0 to 5 centimeters, that 5 centimeters isn't the slant height. 5 centimeters is that.
It's the perpendicular height, or the vertical. It's also, a lot of times, choice of variable can be really important too, and in particular, where you're measuring from.
Like, what are the different possibilities here you're choosing?
One of the possibilities, because you just mentioned measuring from the bottom up to the top, so measuring the height from the bottom to the top, but I could also measure from the top down to the bottom. So I could think about looking at the pieces of paper from the top down to the bottom, or from the bottom to the top.
Okay.
When we get into like whatever particular slice we're looking at, the similar triangles we're going to end up with are this one, and then the larger, the blue one. And since this isn't part of the smaller triangle, and this is basically from experience, from doing a lot of these, I know that it's going to be easier to think about this length instead of this length.
Nice. That's definitely a mathematician habit of mind, right?
Right. And I certainly we could work through the problem measuring from the bottom up, but it's going to be slightly more messy algebraically. But certainly valid. So if I'm choosing my, I guess I'd call it my independent variable, my input variable, is going to be position measured from the tip.
Okay.
So at a particular height h, then I'm going to have height h here. Then this is 5 centimeters. And so by similar triangles, if I call this measurements here, if this is b, which is also going to be this distance, because we cut right down the middle, it's this length.
Okay. Any particular reason for calling it B?
Because it's the base of a triangle.
Oh, okay.
And maybe it's not a good choice in retrospect, because we immediately think base times height now. We're not interested in the area of this triangle though, right? So there's a step where we're taking our position and we're using it to find the base of the triangle, but that base is just one side of that square sheet of paper.
I feel the need to make this joke every time it comes up. It's all about the base.
It is.
Okay.
No trouble. Okay, so from similar triangles, and I can write this proportion lots of different ways, but B is related to H. That proportion is exactly the same as in the larger, which is 4 to 5. And the only thing is to be really careful that it's the position that matters. Base to height, base to height.
Okay, so corresponding parts.
Right. So
how does this help? Oh, because we were looking for B.
we're looking for B. So now that tells me that I have a formula for, at any particular value of H, by multiplying both sides of this equation by H, I get that B is equal to 4/5 H.
Okay.
Okay?
Nice. All right, so we wanted that base so we could find the area.
Right? But we're really looking for volume too.
Because then we're going to add up the...
So let's sketch out where we're going then. So we're going to find the area of the slice, of the piece of paper.
Yeah.
To get volume, we're going to take that area times its height,
That
which is the thickness of a sheet of paper, or actually really smaller.
Yeah, we've been talking about Leibniz's differential.
And, all right, infinitesimally small, right? The thing that got him in trouble with, who was it?
Bishop Berkeley?
Bishop, yeah, Bishop Berkeley. for dealing with the ghosts of departed quantities. So we're going to have, so then the area of a slice is going to be, because it's a square, that's really easy. It's b squared. My b's and my h's look a lot alike. It's going to be 4/5 h squared. So then the volume of a slice is going to be 4/5 h squared dh.
So we could even think about that as kind of a length times width times height.
It is, exactly.
Right.
And then we add these up. So I don't know if you've used the fancy mathematical notation for that, the whole sigma notation or not.
We've been jumping like right to the integral, but if you want to
Okay.
put the sigmas, that's all right.
It does get confusing because one of the problems with the sigma notation is you have to have an index where you have to count how many sheets there are.
Right.
And then that gets confusing because when you go to the integral, then the index goes away.
Right.
So it's this kind of a missing step or an extra step that I don't think helps a whole lot. So to go to the integral, and then we need to know where h goes from. So h at the tip is 0, and the largest value h can take is the entire height, so that's 5.
Okay, so
And-
does the variable matter at all here? Like, so most of the ones we've seen so far have an x for variable, you've got h for variable.
That's a great question. No, the variable doesn't matter at all. It's a placeholder. I could just as easily, instead of an h, I could use an x, I could use a box, I could use something with a question mark in it. It doesn't really matter. What's important is the position and the values that it can take.
So, and then we're imagining it changing over the course of.
Right. So this says we're having h change from 0 to 5, and we're sort of adding up all of these values as h changes.
So at 0, it would be 0.
Mm-hmm.
So that's when we're at the tip of the pyramid.
Right.
Okay, and 5 is all the way down
At the
at the
bottom,
bottom.
where the base would then be 5, 4/5 times 5 would be 4.
So 4 squared, which is what we said before.
Right.
Oh, nice. Okay, and later on we'll have other ways to evaluate this, but we could just plug this into Wolfram Alpha. Do you know, is there a volume formula for a pyramid?
There is. And again, going back to Cavalari's principle, a square pyramid is kind of fun because if there were slices of paper, or sheets of paper, I could shove them all over and the volume wouldn't change. I could shove them all over so that they line up on a perpendicular above one corner. And kind of a fun thing to try is if I had 3 of them, I could put those 3 skewed pyramids together and make a cube.
3 copies of the exact same pyramid. Yeah, I love that. Yeah. So, excellent.
So it turns out then, well, actually it wouldn't be a cube because it's 5 centimeters.
So this would be does it still hold true?
I'll have to think about that one.
Okay.
That's another good mathematical answer is,
Yeah.
I don't know the answer off the top of my head.
All right.
But I do know that the volume is going to be 1/3 times the area of the base, which for us is going to be 4 squared, times that perpendicular height. And I'm going to be really kind of weird about this because all of these things should have units.
Okay.
Right, so everything here is in centimeters. So then this is going to be 16 times 5, which is 8/10, so that's 80. So 80 over 3 cubic centimeters.
Excellent. Yeah, I actually don't know that answer to that about whether we could 3 of those. It's seeming to me that the third one is going to have equivalent volume, but it
Right.
might be a different shape.
I'm gonna have to think about, I know if I had made the height exactly the same, I have actually physically done that and taken 3 square pyramids with the same height and put them together. But I'm probably going to go back to my office and try to make a model and do that.
Well, I've talked about that before, how for mathematicians, usually a problem ends with, oh, and now I wonder, what's next?
Right.
Yeah. Very good. Thank you so much, Clark.
Thank you.
Really appreciate you taking time.
Sure.
All right.